This is a technical session, so we will have presentations from our speakers. And as she mentioned, we are going to look at space science for environmental sustainability. So as we plan to launch our satellites up in space, we should be mindful of the space environment that we are launching our satellite in. So these sessions will look at the space environment and how we can protect our satellite in space. Our first speaker is Dr. Stuart Bennett, and he's going to talk about Earth observation in support of policies for urban climate adaptation. Thank you.
Thank you. All right, well, thank you very much. I'm very happy to be here. Thanks very much to NEOS for facilitating that and allowing me to be here. And the reason I'm talking about this is because of our recent Climate Change Act. So we've spent quite a lot of time in a European context looking at how to create Earth observation intelligence systems to deal with climate adaptation, and I thought it would be useful to share some of that thinking. The picture there is what passes for a joke in the adaptation community, because that's a visualization of a seawall around Venice to protect it from sea level rise. So a lot of this work comes from the Joint Research Centre of the European Commission, but I've contextualized it in a South African way, obviously because I'm thinking a large amount of this kind of value chain and framework thinking is going to be could be very useful given our new legislation that is quite forward-looking with regard to climate change. So what I should do at this stage is show lots of pictures of disasters and talk about the economic cost, but I'm just going to show a simple picture which shows that effectively without adaptation, we are looking at a loss to GDP of in the order of about 10%. And of course, that has many socioeconomic implications, particularly in a society like South Africa that has a high degree of vulnerability. And the other economic aspect, of course, is climate change financing. Now, a lot of this is to do with mitigation and the just energy transition, etc. But it's very important to realize that what I'm talking about is not only the many levels of government through the Climate Change Act, but also, I hope, could be very empowering for the private sector. And ideally, building such intelligence systems, you want to bring in the private sector as users, as providers, as investors. Okay, so let's get a little bit more into the EO. I'm just showing you this. I'm going to be using coastal flooding as my kind of example, but I encourage you to think about whatever your primary hazard is, whether it's drought or heat or fires or whatever. And the key part here is to think that we have a bunch of drivers that we can't do too much about. This is large-scale oceanography. We then have our hazards that would include, in this case, flooding and a whole bunch of other marine-related hazards. But the framework we're going to be using is this risk framework, which if you're in disaster management, you're quite used to. So your risk is hazard, vulnerability, and exposure, and also your ability to respond in a disaster management aspect. So this is just an important concept to grasp. Now, I could spend 10 minutes talking about this particular slide. This is the value chain. And you can look at it either from the left or from the right. If you're looking at it from the left, from a policy perspective, you're looking at how do you get impact from your policy, how do you measure that, what indicators, what highly synthesized indicators do you use, what adaptation frameworks and measures are you using, and then you get into this risk-based decision support tool, which is a combination of the hazard, the vulnerability, and the exposure, and the important thing here is that when I say EO, I mean satellites, models, in situ observations, all of them rolled into one to provide Earth intelligence. So I'm going to go through and look at some of the components of this value chain in a little bit more detail. So our policy driver, this just got very simple for us. In Europe, there's a whole raft of policy frameworks that you have to take into account: Green Deal, climate adaptation, etc. The climate change adaptation plans that are needed at all levels of government is the ability to use evidence-based decision-making around strong intelligence. And you can also see, so if you're in Earth observation and you see paragraphs like this in an act, yeah, that's like manna from heaven, right? There is a policy telling you to do exactly what in an ideal Earth observation world you should be doing, again at all levels of government. Now, let's have a think about adaptation actions. Any Earth observation intelligence, the first thing you've got to do is look at the user decision making, ideally in a way that is agnostic to your technology. So the adaptation actions and the adaptation pathways represent the user decision making, and it's very important to understand them. So here again for coastal flooding, you're seeing you've got grey, hard protection, seawalls, etc. You've got green, which is restoring your mangroves and corals and wetlands. You've got accommodation, move, and you've got information. And this, in a European context, is translated into this typology of adaptation actions. This is the list of the European Commission's adaptation actions. And I won't go through them all. You can see there's everything from governance to finance into the grey, green, blue, etc. The box there are the ones that you can use Earth observation to get some serious traction on. But again, having that catalogue of adaptation actions is a critical first step. You then need some highly synthesized indicators that run across, the ecological, the financial, the political, etc. So when you're looking at how well is my policy being implemented, you don't want to be looking at a kind of building level or a weekly level or something like that. You need these indicators that are synthesized from the decision support tools to guide your implementation and to monitor and evaluate your implementation. Now, here's some real EO. The sharp eyes will notice that this is fairly old census, but let's not worry about that. The main thing is the difference in scale. So if you're looking at hazards, you're generally looking at much larger scales, particularly in the marine environment, kilometers on a daily basis kind of thing. But when you're looking at vulnerability and exposure, you're looking at an urban scale where you're looking at sub 10 meters, probably a bit less often. And understanding the scales of change in both time and space is a very important consideration because those draw on very different kinds of Earth observation with different cost and resource implications. Now, what I'm showing here is a typical land cover land use from a European perspective. This is the core that gets you into vulnerability and exposure parameters. Now, there are capabilities that exist in the South African industry, for example, at GTI, that are leading edge compared to this, multi-scale change detection. But this gives you an idea of how you get to your core vulnerability and exposure. And there is also a measure once, use many. So even though it might be necessary to bring in some of the commercial fleet to get down to urban scales properly, you don't need to be breaking the bank to do it. You can see there's a list of different vulnerability parameters that would then feed a coastal flood impact model, and you can see even an annual revisit is going to buy you something. Quarterly would be great. The modeling aspect is critical, particularly the scenario modeling. So imagine if you have a model, say for flooding, that allows you to put a new theoretical seawall in and see how that changes your vulnerability and exposure, or to change from a 1 in 100 year flood to a 1 in 200 year flood, see how that changes. That then allows you to guide your adaptation actions from a really well evidence-based scenario. So the scenario modeling is an important part of the intelligence. So this is kind of how it all fits together. I know this is a bit complicated, but think of it as expanding outwards. In the middle, you've got more classic Earth observation. That is giving you your risk aspects. You're then looking at that from your key type measures, which are your adaptation actions, and on the outside, you have your indicators, which are telling you about outcomes. So you understand risk, you use that to guide your adaptation, and you use the indicators which are tied to these key type measures, the main adaptation actions, to tell you how successful you are and when you need to kick into a different gear on your adaptation pathway. So if we look at the value chain, here are our key components. It's circular. They need to feed back into one another. So you've got this typology of adaptation actions. You've got the set of policy-facing compound outcome indicators. You have the adaptation scenario models that are very important to guide you. You have this highly quantitative approach to risk through the decision support tools. You have the models in the EO that are giving you information about the hazards, both the historical aspect, the real-time and the predictive aspect. And then importantly, you're treating vulnerability and exposure as dynamic variables in a continuum. These are like Earth systems type data. And that's a departure from perhaps a more historic application of them. And that's me done. Thank you very much.
Thank you very much, Dr. Stewart. Do we have questions on Slido? I don't see any question for you, but I have one question, Dr. Stewart. What are the challenges that you foresee in effectively implementing these adaptation methods?
Well, you would need to get buy-in from the community perspective, which includes both government and the private sector, and then you would need to have the resources, the funding, to build this kind of intelligence system. Now, if the Climate Change Act comes, for example, with a tranche of funding through DFFE for implementation, that might become easier. But certainly getting consensus that this does represent huge value across many stakeholders, and getting sufficient buy-in from government and the private sector are your first key challenges.
Okay, thank you. Let me check if there are any other questions on Slido. I just have a follow-up question, Dr. Stewart. You presented a lot of evidence-based data from the UK or from Europe. Do we have any evidence-based adaptation maps for South Africa?
We have pieces of it. We don't have the cohesive whole. So that's what I was trying to emphasize, is that you need the cohesive whole as an intelligence system to really realize the value. But certainly, so I mentioned, for example, Geoterra Image have a change detection in the private sector that is, it's leading edge. It's probably better than what's available through Copernicus. There are also, for example, the Western Cape disaster management. They obviously, in a disaster management rather than an adaptation perspective, have very, very highly evolved systems. So many of the different parts of this intelligence system are in a reasonably mature or maturing state within South Africa.
Okay, thank you. Ms. Witumelo Makobe, She's going to talk about the role of space weather monitoring in ensuring the sustainability of space-based technological systems. Let's welcome her.
Good morning. My name is Boitumelo, as introduced, and I will be speaking about the role of space weather monitoring in ensuring the sustainability of space-based technological systems. So before I basically go into exactly what space weather is, I'll just give a brief background in terms of what the Sustainable Development Goals are and basically the role of space-based technological systems in achievement of the 17 Sustainable Development Goals. So the Space 2030 Agenda basically emphasizes the role of space-based technological systems in the achievement of the Sustainable Development Goals. So they are basically a build-up from the Millennial Development Goals. So the Sustainable Development Goals, they basically look at some of the shortcomings of the Millennial Development Goals. For example, in the Millennial Development Goals, hunger and poverty were they were one goal, and then in the Sustainable Development Goals, hunger and poverty are divided into two goals. So also, the Sustainable Development Goals were adopted in 2015, so they are basically a summary of the global challenges. In as much as they are a summary of the global challenges, they are also incorporated in some of the national, intercontinental, and continental development agenda. For example, the 2063 agenda also incorporates the Sustainable Development Goals. Okay. So, as I've mentioned, the 2030 agenda basically puts emphasis on the fact that space-based technological systems are very critical in the achievement of the Sustainable Development Goals. But we also need to be aware of the impact that space weather will actually have on the functionality of this space-based technological systems. Okay, so I won't really go much into detail with regards to this slide because throughout the conference, we were given examples of applications of these space-based technological systems from agriculture, going into mapping of floods, also going into mapping of alien vegetation. So also we can see that satellite comms basically contributes the most to the achievement of the Sustainable Development Goals. And then all those applications basically feed into the 17 Sustainable Development Goals. Okay, now to one of the reasons I'm here. So I'll just explain exactly what space weather is. So in simple terms, space weather is how activity on the sun and in space can basically affect the performance of your technological systems, both airborne and also on the ground. So from this, diagram over here, we can basically see that due to space weather, we can have enhanced spacecraft drag that can result in re-entry of your satellites. You can have astronauts being affected by radiation, and that affects basically the health of your astronauts, and then you can have ionospheric effects that can result in navigation errors, and it can also result in GPS signal scintillation, which can also disturb the reception in terms of your signals. You can have high frequency radio wave disturbance due to high ionization in the ionosphere. And then also on the ground, you can have what they call geomagnetically induced currents, and those are basically extra voltages basically in the current that can result in power grids being affected. And then also your avionics can basically, aircraft avionics can actually be affected due to aircraft charging due to the high radiation and the electrically charged particles. Okay, so these are just examples of some of the activity basically that we observe from the sun. So The first one is what we call a solar flare. So basically what a solar flare is a sudden brightening on the sun in the X-ray and the UV band. It takes about 8 minutes to reach Earth, and then it usually affects the sunlit side of the Earth. And then it affects high frequency communication, VHF, UHF, and then GPS and your radars. And then another activity that we look at is what we call coronal mass ejection. And then coronal mass ejections are an ejection that is basically more denser than solar flares. And then it takes about 12 hours to 4 days to actually reach Earth, depending on the speed that it leaves the sun. And then should that coronal mass ejection impact Earth, it can result in what we call a geomagnetic storm. And then a geomagnetic storm is a temporary disturbance in the Earth's magnetic field. And then another activity that we sort of look at is solar energetic particles. This may occur after a solar flare or after a CME, a coronal mass ejection. And then it is high energetic electrically charged particles that can travel with the speed that is close to that of light. And these can affect your satellite operations, and then it can also affect aviation. So this is just to show that with the critical infrastructures that are interdependent and that are connected to each other, if one of those critical infrastructures can basically be affected by space weather, it can result in a chain reaction where more critical infrastructures are basically impacted by space weather, and then that can lead to severe impacts. Okay, so this is just to show some of the significant space weather events since the beginning of the Ice Age. So the first one that I'm going to look at is 1989 geomagnetic storm, which is referred to as the Carrington event. So this is the first storm where there was a 9-hour outage in the province of Quebec due to a geomagnetic storm that's in Canada. And this led to the loss of positional knowledge of space objects for nearly a week. So meaning that your GPS systems were basically affected. And there were multiple satellite anomalies and loss of altitude and signal disruptions that were reported. And then the next storm that I will sort of look at is the 2017 event. So this event was basically high solar activity. So 2 X-class flares were observed, and then there was also a solar particle event. And then that basically resulted in radio blackout, which I will basically speak about in the next slide. And then civil aviation reported a 90-minute loss of communication with a cargo plane, meaning that GNSS and also GPS systems were basically affected. Okay. So this is the 2017 event where 2 X-class flares were actually observed. So this is basically a gauze X-ray flare. It helps us to measure the intensity of the flare. So on the 6th of September, the first flare occurred in the morning around 7 UT, and then this flare resulted in a total radio blackout. So from this ionogram here, you're able to see that you start to see traces in terms of the frequency, but then at some point there is nothing that is recorded. So if this is for the first flare, it lasted for about 45 minutes, and then the second flare, the X9.3, you can also see there's these traces, and then you don't see the traces anymore. This is an indication that there was a radio blackout, and then this is data from Grahamstown ionosonde. Okay, and then, so as I've mentioned from the previous slide, the civil aviation reported a 90-minute loss of communication with a cargo and plane, and also NOAA reported that high-frequency radio used by aviation, maritime, and other emergency bands was unavailable for up to 8 hours. So this was due to these 2 X-class flares. And then this is what we call a D-region absorption map. So this basically shows us the frequencies that are affected whenever you have a solar flare. So in this instance, this was for the X3.7. So we are able to see that frequencies from 0 to 35 megahertz, which is high frequency communication, were affected, meaning that they were not, whichever sector basically uses high frequency communication couldn't use high frequency communication for the period of the flare. And then the other storm was the 2022 February 3rd to 4th February storm. So this is one of the storms that basically helped us to actually understand the impact of space weather on satellite operations. So basically Starlink launched and also lost 38 out of 49 satellites due to enhanced neutral density associated with a geomagnetic storm. And that basically resulted in an increase in drag, and that is what subsequently resulted in Starlink losing its satellite. Okay. So from here, this is a planetary index that we use to just sort of show how the Earth's magnetic field is disturbed. So in most instances, this can reach up to a KP of 9, but we sort of start expecting more impact when it reaches a KP of 6. So in this instance, we see that the first storm started on the 3rd of February, and then it resulted in 2 minor storms intervals, and then this storm had not recovered as yet, and then the second storm then started due to arrival of another CME on the 4th of August, which is what basically resulted in an increase in atmospheric drag, and then which resulted in the loss of 38 out of 49 satellites from Starlink. Okay, so basically this event is really just an indication that even a small storm can really cause like catastrophic effects. Okay, so we recently had the biggest storm in 20 years. This storm was observed on between the 10th and the 13th of May 2024, and this was due to the arrival of multiple coronal mass ejection that occurred from the 6th to the 8th of May. And you can see here, this is what we call auroras. So basically when the coronal mass ejection leaves Earth, it leaves the sun, it actually has some energetic particles that will come into the upper atmosphere and react with the gases in the upper atmosphere, and that will result in the beautiful colors that you see over here, depending on which gas is present the most. Okay, and then this is just to show the economical impact. You can see if there is a GNSS outage, it could cost at least $1 billion a day. So basically, space weather monitoring is very important, because I don't think any country actually wants to lose this amount of money per day. Okay, so I'll just go to. Okay, so this is the Space Weather Center that is located in Hermanus, and then South Africa through SANTA has been designated as a space weather information provider for the International Civil Aviation Authority. So basically this means that in the same way that the civil aviation require terrestrial weather, they also require space weather information. In high frequency communication, in radiation exposure, and then in also GNSS navigation. Also, the Space Weather Center is it's 24/7 operational, and then ACAIO compliant and also ISO compliant. And then, so basically the timely availability and reliable and consistent space weather information is essential in order to mitigate the impacts of space weather. So in a nutshell, it is very important that space weather is monitored. It is important that there are predictive models in order to basically help us to predict if there are going to be any severe geomagnetic storms or any solar flares in order to protect critical infrastructure. Thank you.
I'm checking. Thank you very much, Witumelo. I don't see any questions on Slido. I saw you've presented an interesting event, the Starlink satellite. So what do you think the SANSA can do in terms of space weather monitoring to mitigate such impact from happening again?
What SANTA is doing currently, we are forecasting, and we are also monitoring space weather. And I think improvement in some of the predictive models will basically, aid in mitigating some of the impacts. Yeah.
There is another question. There's one question, two questions we just came, or three. Okay, so the first question, has there been any studies relating to space weather and earth weather?
Okay, so space weather is basically from 50 kilometers upwards, and then we also have terrestrial weather from 50 kilometers downwards. So from some of the talks that we've heard from our researchers, I know that there's gravity waves in atmospheric, like in the terrestrial weather. Somehow they are associated with what happens in the ionosphere. So that's just one of the linkages that I can, think of quickly.
Another question. Maybe you can read it out. Okay. Another question is, how does the South Atlantic anomaly affect satellites?
Okay, so yeah, the South Atlantic anomaly does have, a number of electrically charged particles, and I'm fully aware that satellites actually do pass through that, and I think that was taken into consideration during the design. So I haven't really seen any information of maybe a satellite being affected by the high radiation there. But I think that the life expectancy thereof would be affected because it's continuously passing through an area of high energetic particles. So if the life expectancy was like 10 years, maybe it can be decreased by like 2 years because of the interaction with the electrically charged, the continuous interaction with the electrically charged particles.
And the last question for Witumelo is, are we able to predict the impact of our sun on climate stability? On climate stability. Climate change. Yes.
Okay.
Can you talk about the if there's relationship between space weather and climate change?
Okay.
Yes.
Okay, so that's a very difficult-ish question. But I've got a background in atmospheric science, so basically terrestrial weather, and I've not seen as yet if basically space weather has some sort of impact in terms of terrestrial weather. I think that's the best I can answer the question.
I think we can just take this one last question and we can continue to the next speaker. How does the information about space weather translate into application?
Okay, so for example, with the Starlink issue, what had happened is that they launched their satellites into, the first entry was at 210 kilometers, and then due to space weather, now they've changed it to 300 kilometers. So at the current moment, we are at what we call solar maximum, so they've used that information to sort of help in their mission planning. So that's one example for application.
Thank you. Okay, I'm going to call the next speaker, Mr. Laven Naidu. He is going to talk about estimating till carbon stock across Gauteng using a multi-sensor remote sensing approach. Thank you.
All right, thanks a lot. Good afternoon, ladies and gentlemen. Good afternoon, ladies and gentlemen. Can you hear me? Good, great. So thanks a lot for having me. My presentation today is on estimating teal carbon stocks across the Gauteng province using a multi-source remote sensing approach. And I would like to acknowledge my co-authors and collaborators here, Dr. Heidi van Deventer, as well as Sisipo Ngewe, my MSc student as well. So I just want to quickly state what is the GCRO quickly. So the Gauteng City Region Observatory is basically a research or institutional collaboration between the University of Johannesburg, Witwatersrand, as well as the Gauteng provincial government and the organized local government in Gauteng. And our main objective here is for basically encouraging policy-oriented research. And that's looking at medium to long-term decision-based and research or applied-based research, and trying to link that to decision-making within the Gauteng province as well. So our main focus is both on understanding the conceptual ideas of the Gauteng province and how it works, as well as looking at developing quantifiable matrices in order to quantify very complex societal problems as well. So the actual work that I'm actually going to be presenting today was based on a conceptual idea which I came up in terms of developing a carbon atlas for the Gauteng city region. And that was kind of motivated by the objectives of the city of Johannesburg, city of Tshwane, and Ekurhuleni's drive to become carbon neutral by 2050. So in order to become carbon neutral, people need to, or basically researchers need to understand what is the quantification of the carbon emissions as well as carbon sinks. So where is the carbon actually stored and what sort of carbon is actually being emitted? In order to do that, we need to actually look into leveraging the use of remote sensing technologies and integrating multiple remote sensing layers with AI machine learning algorithms as well. In order to understand the concept of carbon as well, I decided to use that approach or conceptual framework known as the colors of carbon, a very simple process in which different colors are allocated to different contributions or aspects within the carbon spectrum, looking at the carbon sinks as well as carbon sources. A quick one in terms of that is in terms of green carbon is basically the carbon stored in trees. Teal carbon is the carbon which I'll be talking about here, that's stored in wetland vegetation. And then you look at blue carbon, which is stored in sediments, and as well as seagrasses in the ocean, not necessarily applicable to the Gauteng city region. And finally, brown and black carbon, which is basically the emissions, the inorganic and organic carbon emissions. So that's kind of the focus of this particular presentation. So why look at teal carbon? So teal carbon is a very small entity across the global landscape, even smaller within the South African context. 5 to 8% of the global land surface is actually occupied by teal carbon, but they actually contribute to 30% of the soil carbon reserve globally. So a very small area contributing very greatly to the overall stored carbon pool across the planet. And in terms of an important concept here is that a lot of these wetlands are basically, or teal carbon bodies, are super sequesters, which means they can actually extract or sequester carbon. Basically, a smaller area of this teal carbon is actually extracting a much similar area to large trees and forests. So that basically, they're highly super efficient in terms of the extraction of carbon from the atmosphere. And it's very important to actually monitor and quantify them within the Gauteng city region, and obviously South Africa and the planet at large. So the main focus of this actual talk will look at the mapping, the spatial distribution of this teal carbon concept, or this metric in grams per meter squared across the Gauteng city region, using both multi-seasonal, regionally collected field data, leaf area index measurements on the ground, as well as a fused Sentinel-1 and Sentinel-2 approach within a random forest machine learning algorithm environment. And then we're going to use a variety of basically hydrogeomorphic units, as well as ecological conditioning and threat level classifications to actually understand what's actually happening to these teal carbon sources. This is just a quick diagram over here on the left, which look at the different HGM units and how they're kind of defined from a spatial context in the landscape. So a lot of this work is kind of going to be presenting here is going to be motivating the use of a multi-source, multi-seasonal, and a regional approach. Why use all these different technologies and different concepts? And this kind of emerged from some of the results from the past research objectives, which looked at mapping wetland vegetation and AGB across the landscape, above ground biomass. And some of the outcomes in terms of that is that we found that within very localized areas in the grasslands, using Sentinel-1 and Sentinel-2 was more or less sufficient to actually estimate carbon or teal carbon using basically very simple matrices such as backscatter and reflectance values or reflectance bands in combination with leaf area index measurements on the ground. We can actually use that to derive models which are comparable to WorldView 3, which is actually quite something, but obviously not matching the high resolution of WorldView 3. In terms of a multi-seasonal approach, one of my MSc students was looking at monitoring the seasonal compositions or seasonal variations of carbon across these different grassland ecosystems, and found that there was a significant difference between summer and winter above ground biomass or carbon ranges. And so from a modeling perspective, if we choose to kind of extract measurements of above ground biomass across the different seasonal variations, as well as different regional areas, we can actually increase our calibration and validation data sets for our model. So actually really boost our ability to predict this from a greater geographical region. So this particular study focused on 3 major sites for aggregating data sets from 2017 all the way to 2022, looking at the Coleman wetland, which is up here in Pretoria, all the way to Christmasmere and to Vredepan, which is in Mpumalanga, and Hogsback, looking at more or less Afromontane-based wetland systems here, which has one of the more lower ends of above ground biomass or carbon measurements. So these particular statistics here basically include the different variations of our minimum and maximum range of carbon which we collected from our field samples on the ground. And this was actually used to calibrate our different models. So in terms of our modeling methodology, I'm not going to bore you with the actual detail here, but it was a 2-step random forest modeling approach in which we used our field data that we collected in the field with these little quadrants. We cut a lot of plots, about 130 plots across these different study areas in total. We extracted the actual biomass, we dried it, and we weighed it. We actually kept that or collected leaf area index measurements using a lycometer, also in conjunction with the collection of the above ground biomass. We then extracted Sentinel-1 and Sentinel-2, basically remote sensing attributes from that, and we combined it into a random forest model using a 65%, 35% training and validation approach. And then we used validation statistics such as R-squared, RMSE, and standard area of prediction to kind of validate the model in terms of its effectiveness. In terms of the actual mapping, we had to kind of extrapolate from the LAI measurements, just because they were localized LAI measurements. We had to create another random forest model using basically Sentinel-1 ratio variables, as well as spectral vegetation indices, which are based on the red edge channels, such as red edge NDVI, EVI, basic chlorophyll index, and the inflection point as well. So we can combine that to create our own different LAI-based random forest model to produce a layer which we intersected with our input parameters here to create our teal carbon product. And we converted the actual extracted above ground biomass to carbon by using a correction factor of 0.5. And that was used to create our map, which I'll show you shortly. So these are some of the validation results that we got. The figure on the left looks at basically the XY scatter predicted versus observed from our model. And we can see a very good fit across the different above ground biomass or carbon ranges. And unfortunately, there is some level of basically a noticeable underestimation on the top end, but the bottom end of the carbon range estimation is actually pretty decent. The figure on the right is basically the LAI model, which we use in the actual modeling process with the teal carbon model, and we're seeing a bit more improvements that needs to be done here. So we're getting a massive underestimation, actually overestimation at the lower LAI range, as well as an underestimation at the high LAI range. And that indicates that using an empirical random forest approach, in terms of estimation of LAI, we should be actually looking at more advanced techniques such as radiative transfer models or the ProSail model, which you can possibly use to improve this result, which will ultimately improve our model and hopefully extrapolate that with greater detail. In terms of the actual map that we created of teal carbon, and these are clipped towards using the National Wetland Map 6. And what we can find here, actually follows a very nice pattern in which there's a distinct variation between the south of Gauteng and the north of Gauteng. So we're getting much lower teal carbon values in the south, which where is basically the intersection with the grassland biome, and much higher values to the north, where the savanna and bush encroachment and bushveld ecosystems are kind of emerging as well. But what is also surprising to note here is that within the city region, in which is a very dense population of suburbs and different informality and formality, we're getting the most densest pockets of teal carbon. And that's examples such as Colburn, Blesbok, Spruit, as well as Ritvlei, and other areas close to or just south of Soweto as well. So these very, very dense pockets of teal carbon is actually at a high risk of anthropogenic degradation and impacts on those ecosystems. Just finally wrapping up, based on the hydrogeomorphic units as well as ecological condition and threat level analysis that we did, we found that basically 71% of the stored teal carbon was found in unchanneled as well as channeled valley bottoms, which is a type of HGM classification, and 70% was found in seeps. And the rest of the percentage falls in much smaller HGM unit types. But what is important here is that they kind of amass to close to 8.8 million tons of carbon being found in these two main types already, which is quite a significant amount of stored carbon in these entities. When looking at the different threat levels, as well as ecological conditions, we find between 60 and 66% of these ecosystems and stored carbon are actually not protected and are critically endangered, which is a very, very important societal as well as government issue that needs to take place, in which policies are taken into place to actually improve the protection of these much needed teal carbon reserves. So in terms of just finally wrapping up the conclusions here, this study produced the first ever basically teal carbon product, a map of Gauteng, which basically in combination with green carbon as well as soil organic carbon, we can actually create a very good representation of the terrestrial carbon store within the Gauteng region and offset that against our emissions. We can actually find out whether these different cities are carbon neutral or not. We found out obviously the unchanneled, channeled as well as channeled valley bottom and HGM units occupied 71% of the carbon store, and approximately 8 million tons of the 12.6 total reserve is actually critically endangered as well as not protected. So in terms of moving the way forward, in terms of our analysis, we're going to improve the model or the modeling process by actually using RTM or radiative transfer based modeling to improve the LAI estimation, as well as using very advanced airborne data sets, which the team and CSR talked about yesterday, in terms of using that as an upscaling factor in our modeling process, in which we can use these to actually create more training sites for our satellite-based model. And finally, extract the teal carbon estimates for more localized ecosystem functional group types. And with that, I would like to thank you for your time. And if you have any questions, just please send it through to my email address. And please feel free to subscribe to our mailing list at the GCRO as well. Thank you.
Thank you very much, Mr. Naidu. Let me check if there are questions on Slido. I don't see any question. So maybe we will move to the next speaker, and then if there are questions which comes after that, then I will let you know. Let's thank the speaker again. The next speaker is Mr. Phila Sibanze, and he's going to talk about leveraging remote sensing data set and deep learning algorithms for flood probability and risk assessment. Thank you.
Thank you. Thank you. My name is Phila Sibanze. I'll be presenting to you a study we conducted at Port St. John's using remote sensing data sets, integrating it with deep learning-based approaches in developing a probability, a flood probability and risk map. Just to give a brief background of the flood risk, a holistic color view globally, is that the flood risk determines determined by estimating the extent of loss, number of lives lost, property damage, and disruption to economic activities. Basically, when we are determining the flood risk, we look at what were the effects that have been happening on the ground in relation to property that have been damages, life that have been affected. And the CREED in 2010 recorded disasters that happened at a global scale, and the majority of those disasters that happened were flood-related disasters. And within those recorded disasters, a total of 189 million people were affected. And that amount was the highest in relation to the previous decade in comparison to the affected people within that time frame. And bringing back to South Africa, 2022, which I call it the year of disasters, in January in the Eastern Cape, Mtansane, the second largest township in South Africa, there were 14 people that were killed by floods. And I'm sure you would also recall within the same year in April in KwaZulu-Natal, 435 people were also killed by the floods in KwaZulu-Natal. And those floods, unfortunately, the focus was more on on KwaZulu-Natal. They also spilled over to the Eastern Cape, in particular Port St. John's. But in total, the estimated damage of those floods in South Africa was about 10 billion rands. So what this is saying to us is that there is a call of action to start improving or developing systems that will actually be address some of these challenges. And what we've picked up is that globally, not globally, but within developing countries, including South Africa, we need to have systems that will be able to respond to emergencies, in particular disaster-related emergencies. So the aim of the study that we conducted was basically to use geospatial data, applying deep learning-based algorithms, in this case, convolutional neural network, in developing flood probability and risk map in the case of Port St. John's, because it's one of those areas in South Africa, a small coastal town that is increasingly being affected by floods. And to achieve that, we just highlighted two objectives to achieve our aim. The first one is to use different data sets that are influencing the occurrences of floods, of course using the deep learning-based approach, and also applying it within the context of Port St. John's is to use the fully connected convolutional neural network approach. So in light of the background that I've just given, we also like to highlight the problems that are also identified in Port St. John's. And we found that in the past decade, there have been an increasing percentages or rate of rainfall in the area, which leads to surface runoffs and also a lot of infrastructure being affected within the region. And those occurring floods within the area, they're consistent with the impacts of climate change globally and their variabilities. And of course, the inadequate presence or availability of ground-based data. And once again, this also is a justification that we need to take action. And if I can draw into the words of the Chief Executive Officer of SANSA, saying that as much as we come together as brilliant minds, we also need to take action in addressing socio-economic issues. And this is one of those examples where we are bringing back, or we developed a system, a geospatial system that addresses or seeks to address the challenges that are faced at Port St. John's. And the significance of the study when you look into what is happening globally in the context of flood risk assessment is that it taps into the usage of artificial-based approach, integrating it with geospatial data set to basically answer or respond to the challenges that we are facing. And the approach that we adopted, the fully connected neural network approach, has proven amongst the studies that have been conducted globally to produce acceptable and high, having a high accuracy in terms of predicting floods. And the model that we developed used 13 geospatial layers, multi-source layers. That includes the height, above Nile drainage, total water index, modified normalized different index, land cover, to mention but a few. But all of these layers, they were combined together and ingested into the model so that it can start to understand the patterns and the patterns of how all of these layers come together to identify areas that are susceptible to floods. And while doing that analysis and assessment, we really identified the gaps within the area, in particular our area of interest or research, was that we had to develop a system that was using AI to respond to the challenges that we are facing, in particular when it comes to flood risk assessment. And having said that, we also identified that there was also a lack of integrated multi-source approach that is using artificial intelligence in this space. And another aspect or another point was that there's inadequate innovation in terms of using the systems and the technologies that are available to us in the modern day of AI to respond to disasters, in particular floods. So this is Port St. John's, which is situated at the mouth of Umzimvubu River, which has its source in the foothills of the Drakensberg Mountain, bordering South Africa and Lesotho, and stretches for about 400 kilometers before it dips into the Indian Ocean. And Port St. John's is sitting right there at the adjacent of this Umzimvubu River, stretching 400 kilometers upstream. So you can imagine the size of the catchment upstream, and all of that catchment, the water coming from that catchment dipping into the Indian Ocean. And when there is a high tide, what happens to all of that volume of water? Hence, Port St. John's has been significantly affected by floods in recent years. And Port St. John's, it has a population of not less than 200,000 people, and the majority of the population in the area is between the ages of 15 and 64. And a small percentage is consisting of pensioners, which is 6%. And when you look at the housing structure, a third of the housing structure is informal settlement. And one of those informal structures, including informal settlements. One of the informal settlements is the Work Green informal settlement, which is also sitting at the high risk zone. You will see that area as I proceed in my presentation. And the climate is characterized by humid and subtropical climate. Basically what this means that even in the driest season, this area receives rainfall. Hence, it is also one of the areas that is affected by floods, even in the driest, or one of the areas that receives rainfall even in the driest season. So, the crux of my speech, of my talk, is based on this diagram. The model that we developed, which is purely on the cloud, and we used Google-based resources, where Google Earth Engine basically was used to extract some of the data set, including the rainfall data from chips. And we used the Google Colab, which is a Python-based programming platform. And that platform, actually, it is flexible in terms of the functions you can use. We used the HiRAM and the Tesla T4 processing unit, which is optimized for deep learning approaches. And we collected ground-based data that we used to identify the areas that have been proven to have been affected by floods. And all of that data sets, including the one from Google Earth Engine, we stored it in the Google Drive. And through the Google Colab environment, we started to ingest the data into different, separate the data into different sectors where we adopted an 80-20 approach, where we were training the data and also validating at the same time. But this is the data sets that we used, the different layers that we used. So I'll just speak faster because of time. And so this is the entire model where all of the data set this side was ingested and into multiple layers, including the convolutional layers and the max pooling. The convolutional layers, they basically look at the different spatial properties within the layers. And the max pooling just reduces the spatial dimensionality of the features identified, and subsequently it runs through all of these layers and subject it into a flattening layer, which prepares it for the fully connected convolutional layer, which identifies the features of interest in terms of, is this a flooded area or not a flooded area, and subsequently producing a binary raster or a binary feature showing flooded and non-flooded areas. And we subjected, after that, we then looked at the areas produced by the model, the performance of the models, and we realized that the areas that were identified as flooded, they were basically indeed areas that have experienced flooding in the area. And the evaluation and validation of the model was subjected to a number of evaluation metrics, but I also want to speak about these two, where you can see that the laws, at first the model starts to train itself, and then it looks at the predicted versus the actual values, and you can see there's a correlation between them. But once the model starts to overfit itself, it learns that it is now modeling outside the norm, and it recalibrates itself in such a way that it proceeds to do appropriate modeling. And once again, also like to take you to this diagram here where the model accuracy increases, but what happens is it starts to do what we call an overfitting. And it doesn't overfitting, and we calibrate it in such a way that if it doesn't overfitting for 10 iterations, it must revert back to its point where the model was not overfitting, and that we call it an early stop approach to prevent the model from overfitting. Running out of time. So let me just get into this slide. So in conclusion, the model that we adopted basically revealed that the deep learning approach using multivariable approach was successful in Port St. George in identifying, or rather classifying, flooded and non-flooded areas with an accuracy of 98%, even though it was deployed on the cloud. It managed to get that type of accuracy. And the probability map revealed that the low-lying areas identified by the model were actually areas that have experienced flood in recent years. And the findings, of course, can be applied and upscaled into larger catchment areas, hence providing information for decision makers and influencing policy change within this domain. And the study can also serve as a baseline for changing policies and developing pre- and post-event strategies within the space of flood risk management. Thank you very much, and I thank you for your time.
I don't know. You have a few questions. Okay. Thank you very much. There are a few questions on Slido. The first one, I think, is just a comment. Very excellent work on environmental scan and the literature survey. Paper ready for publishing. And the second one is the CNN model developed production ready for deployment or deployable?
Yes, very ready, 100%.
He said it's ready, it's 100% ready. And then are there plans to implement this in PSJ, or does this just end as another brilliant scientific methodology?
It's a good question. We intend to take it back to the disaster risk, to the disaster office in Port St. George, because we're working closely with them in terms of engaging with the communities even also after developing the model to go and validate it using ground-based information. So it will be handed over and also information shared with the disaster office at the office of the Port St. John's Municipality Office.
Okay. Thank you very much. Let's thank the speaker again. The last speaker of the session is Ms. Nkosinati Masango. She's going to talk about analysis of ionospheric storm effects based on GPS and ionoson data during geomagnetic storm. Let's thank her. Let's welcome.
Oh, okay, thanks. Good afternoon, everyone. And yeah, I'll just explain what I normally do besides being a forecaster. So I'm also doing a project on the side to get to see if we can improve the space weather department from Hermanas. And another thing, yes, it's not a mistake. On the program, that's where the mistake is. I am a woman. It is Miss. It's not a Mister. Because I got that question a lot regarding my name. No, it is a Miss. Okay. Okay. Yeah, so I will try to explain my project and try to make it as simple and as very entertaining as possible because after all, it's a Friday. So yeah. So in a nutshell, so as the previous speaker spoke, who happens to be my colleague, we are interested in the upper region of the Earth's atmosphere. So that would be like 50 kilometers above and going forward. So one of the other regions that we look at mostly or layers would be your ionosphere. So basically, what is your ionosphere? So your ionosphere, basically, it's a layer or a region that extends from 50 to 1,000 kilometers, and in that area you get free electrons that are just there all the time, and then also now it happens that it is partially ionized. So what happens is that with the ionosphere, it's not necessarily the same all the time, so it's not uniform. So it changes. So there's reasons why it changes, and those reasons they subjected to your day-to-day variations in the ionosphere, your seasonal variations, your latitude, depending where you are, whether you're in the equatorial region or mid-latitude or high-latitude regions, and it also depends on the solar activity, so what's happening on that day, whether you're on solar minimum or solar maximum. But also we do have some processes that happen on a day-to-day basis. So on a daytime, we have what we call a process called photoionization. So that's simply when your neutral atoms now, they disconnect and then you have ions, free ions and electrons. But then later on at night, the opposite happens and that's called recombination. So that's when now your atoms now connect and it happens during the night. So on this image you can see, it's just a typical schematic diagram of what it shows you during the day, what it will look like versus during the night. As you can see, some layers, especially like your D layer, it's not there anymore. That's because of the in simplicity, that's your day-to-day ionization versus recombination processes happening. So, next. How do we measure the ionosphere? So we have instruments that do measure the ionosphere. We use a ground-based instrument, which is called the ionosonde. We have one in Hermanas at Sansa at our premises. So this is what it would look like. So what is great about the ionosphere is that it gives you a detailed, so to say, a detailed description of what your ionosphere looks like at different levels, as you can see. But it's also very limited because now the problem with your ionosonde, it does not necessarily go up to the altitude of your GPS or of your satellites, which would be 20 kilometers, 20,000 kilometers and above. But it is something that we really admire and use a lot. So how it works, basically, you have like a pulse that they send out, and then what it does, as it travels through your ionosphere, it maps the frequencies at different altitudes. So if you can see here, this would be your height versus your altitudes, and it will record what would be your frequency at that height. It will keep on doing that until it reaches what we call critical frequency. So that's the highest frequency where your pulse can pierce through the ionosphere, and that's where it ends, at your F2 region layer. But we now, since we want to study what the ionosphere does and it extends all the way upwards, we need another instrument or another data set to try to compensate to see, in general, the whole surf, what it does. So in this instance, we'll use what we call your total electron content. That's just a parameter that we use to study the ionosphere. So what happens is that since now you are limited in terms of your ionosonde, you'll use your satellite image, your satellites that you have. So from also the previous session, they did speak about what your satellites do. So your total electron content, like I said, it's a parameter that we use to study the ionosphere. So what happens there is that it's just, if you look at this image, it's just the number of free electrons that you find in that column of, it's like a cylinder. If you think about a cylinder, that's the number of free electrons that you would have on that cylinder, inside that cylinder. And how it's done is that they use the two frequencies, your L1 and your L2. So what happens is that they measure the time delay. So the time delay it takes for the satellite signal to move from your transmitter to your receiver, that will be proportional to what is your total electron content. So that's what makes it a very good parameter to monitor the ionosphere. So that's what they normally use. So coming to the project itself, what we want to see is that as much as, so this is basically what your GPS tech would look like. So what we basically want to see is that by using these two instruments, your ionosonde as well as your satellites, that you derive this TEC, how it responds at different levels. Because the problem is, like I said, with your ionosondes, you can only see up to a certain altitude, which means you won't be able to see what has happened on anywhere above from 800 or 1,000 kilometers, depending on how it works. So now, what we want to see here is now you want to see what we call a plasmaspheric tech. So plasmaspheric tech, it's just tech that you find in your beyond your ionosphere. So the importance of this project, what it would do is that it separates your tech. So instead of just looking at it at your GPS tech, as much as your GPS tech, you get to see everything from 20,000 kilometers right above to where your receiver is. You cannot necessarily see it in detail. So you want to separate these to be able to determine these ionospheric storm effects. So ionospheric storm effect, in simple terms, is just when you have an increase, which is called a positive ionospheric storm effect, or a decrease, which is your negative, in your electron density. So that's what we want to look at. And now we also look at the different categories of your storms. So here we do get different categories of your storms so that at least you know by using this index what they call the DST. So DST is called your disturbance storm time. So that's just one of the indices that they use to make sure that they want to see when the storm has started, where we have your sudden commencement time, your main phase, and your recovery phase. That's where you can clearly identify these. So now, how does this work? In order for you to be able to know that, okay, this is when the time or when the storm has happened, you need to make sure that you understand what the atmosphere does when there's no storm. So that's when you get what we call your monthly median. So your monthly median would be your quiet time variability. So this would be, for instance, if you look at on the figure, the blue line here, that's like what your monthly median looks like. So how I would explain it, it's like for you to be able to say that someone who was once poor and they are rich and they've changed, you need to see how they've behaved when they are poor, you see. So we are trying to do something like that. So it's like a background, it's like a reference. Ne? Yes, so that's what we normally do. Right. Okay, I'm sorry, I'm gonna have to turn my back. Apologies for that. So yeah, that's what we normally do. So this would tell you roughly what you would have expected your ionosphere to be doing when there was no storm, more or less. So you can use it as a reference so that you can be able to at least see whether there was an enhancement or a depletion in your electron density, in this case your TEC, which is your total electron content. But then also you need to be able to quantify that. That's when we come across what we call deviations, which is just a percentage that they use, which is done by this equation here. It's not as simple as this. I simplified it. It's very complicated, guys. This is serious things. But yeah, it's not like that. So that's what you want to see. So these are the thresholds. So these thresholds where you can see it's a plus minus 45%. So what these thresholds basically would tell you, for instance, these would be when there was no storm that was happening at the time. So this is where your DST will look like. And this is when you have that, when I told you will have an increase in your DST where it's your sudden storm commencement coming in, and then this would be your main phase. So your main phase will be where you get, your DST would be at its maximum. And then you can see where the recovery rate is. But you can see that, for instance, when there was no storm, both your monthly median and your GPS and your INOS1 tech values at the time, they were resembling what your monthly median would look like. But as soon as you start getting disturbances, you can see that there is some changes where you have a positive enhancement, and then you have a negative enhancement, but that you could quickly identify it with numbers. So it's not enough for you to say that, okay, we had a storm, but by just looking at it, it's a positive or a negative storm effect. You need to have some numbers to quantitatively be able to say, okay, this is a storm or a positive or a negative storm. So you can see it by this. So as soon as you can see your enhancement increases, your deviation starts to move away from your thresholds, which is your plus and minus 45%. So the 45%, the plus and minus 45% is what we got from literature. But also now, since we have separated it, now you want to see what would also be your ionospheric tech. If looking at your ionospheric tech also separately, like here, would it also have the same deviations, or will they be different from what you see? So here you can see a clear positive deviation, and it follows more or less the similar pattern of a GPS. And also here you can see on the following days, you can see you still have a negative storm effect, where you can see that your deviation still resides or live within your, have exceeded your threshold. So that's what we look at. And then you can also see now, as much as it's for the same year, if you must notice, it's for the same year, but for different months. Here you can see it's in March, and then this is for also June. But you can see that also your TEC, which is your total electoral content, has decreased compared to what it would have looked like in March. But you still can see that these thresholds, they still hold. So it needs to hold. It really doesn't matter. So of what they do. So the next step would be in this, since we have established also that, okay, from literature, your GPS tech deviations are within the plus minus 45%. You also can use the deviations for the same deviation threshold as your ionospheric, for your also ionospheric tech as well. So we want to see in future what would your plasmaspheric deviation look like, and if you can quantitatively be able to study the mechanism, because at the end of the day, if you make a model, you want to make sure that you are able to capture the duration of the storm accordingly, to make sure that perhaps that if they don't respond the same, you might be able to miss other points of the storm when it happened. So the whole point of this is to just get a detailed structure of what your ionosphere looks like in terms of tech, what it looks like at different levels, and to be able to determine the mechanisms of what roles and contribution it would be at different levels. So what would happen? So for instance, if we are able to determine these mechanisms that drive the storm, then these are some of the parameters. Once we get someone who is very patient and can do modeling for us, then that person will be able to use those as like parameters to be able to try to make a model where we can forecast and be able to see what happens that when a certain mechanism dominates at a particular point in time of the storm, what could it possibly do? Would it, for instance, prolong the positive storm effect? Would it make it shorter in terms of duration or intensity? So that's basically in a nutshell what we do. And I hope you enjoyed my presentation, because I enjoyed it. Thank you.
Okay, thank you very much, Nkosinathi. Let me just check if there are questions on Slido. I don't see any question here. Just a question from my side. Are there any plans to develop like early warning systems within the Space Weather Center for improving our monitoring?
Yes, they are. Currently what we have is the near real-time tech. So it just monitors what the tech is doing at near real time. So that data can be used as archives to try to be able to see what happens when we have these different conditions. Because you, like I said, your ionosphere will vary depending on what's happening. So when you have maybe high solar activity, you now have an archive of what it will look like versus when you have low activity, and then that can be used as your inputs or your initial conditions in the model to try to be able that when we see these storms far in advance, what can we expect? So thank you.
Let's thank our speaker again. There is one question which came from Tato to the whole panel. So I'll just ask Mr. Naidu to start responding to that. Can these data systems and algorithm models be utilized in human settlements, planning, and also in the design of civilian architecture?
Thanks a lot for that question. From my perspective, all the models that are kind of built, they're built with that idea of having a societal impact in mind, because a lot of these data sets and models that we create, it's basically validated in real world conditions. So from my perspective, the work that I'm doing, it has that societal impact in it. And to be able to quantify that is another sort of social geography question that we can also move into. But in terms of the models and the uses of the models, I think once they are basically trained and ability to extrapolate it across different geographical timeframes, as well as spatial extents, if models are robust enough to do that, I feel that they have a good societal impact throughout. Yeah.
Okay, thank you. Any other person want to respond to the question?
So that's pretty much directly what these kind of adaptation intelligence systems are doing, is reducing the risk or increasing the resilience primarily of human settlements. So yeah, it's very relevant.
Okay. I think you want to speak? Yes.
Yes, definitely. The systems that we develop, ultimately the goal is to make sure that they benefit the society directly. So in particular, the early warning systems. And what I would add to that is in the context of localized areas, the system should also direct the information to those that are at high risk at the moment of the risk being identified, to cut out the middlemen. For instance, if there's a situation where there is a risk in a certain area, there mustn't be a middleman where the information is transferred to and then later sent into the people that are affected on the ground. It must be directed immediately to the people on the ground to make immediate decision, because they're the one that will be affected directly by the situation that is about to unfold in relation to the systems.
Okay. Thank you very much. I think we should thank our speakers again. I will hand over back to, yes, to you. Okay.
And as we hand over these thank you gifts to our speakers, a round of applause to all of them, please.